So, hello to everyone. We are in the second e-YEG webinar series from IEG and YEG. After the first successful presentation of the first e-YEG, we're going to the second one with our invited speakers, Tim Nash from PSM company and Dr. Sarah Bastin from the University of Auckland. So I would like to inform you that the presentation will last for 45 minutes approximately, and it will be a time for questions and responses from the presenters after their presentation. So please, if there are any questions, please put them in through after the presentation of Tim Nash, firstly, and secondly, with Sarah Bastin. In order to start, I would like to ask you to mute your microphones and turn off your cameras in order to be able for the presenter to be smoothly in his presentation. Firstly, I would like to welcome our first presenter, Tim Nash. Tim, can you turn on your camera, please?
Sure.
Hello. So,
hello.
Tim has been graduated from University of Canterbury in 2003. He receives his bachelor degree and master degree from University of Canterbury in New Zealand. He joined the PSM company and he's working as a principal engineer geologist. He has been worked in several projects, including infrastructure projects, including road and rail, tunnels, mining in Australia, but also abroad. His work experience includes pre-feasibility through to detailed design and construction phases of project development. Tim, your space is yours. You have 45 minutes. Please share it.
Thank you very much, Stratus. So I'm not, can everyone, you see that all right, Stratus, and everyone else?
No, not yet.
Sorry, how about that now?
Yeah, just starting sharing your screen right now.
Sure. Okay, how about that?
Yeah, that's nice. That's nice. The space is yours, Tim.
Okay, good stuff. Thank you. Well, firstly, thank you for having me on to talk about what I do like to talk about, which is engineering geology. The theme for today's talks is investigation of soils. And when I was putting this together, I wanted to put a bit of a different spin on what would be typical or characteristic investigation of soils, which an engineering geologist might do. I also wanted to introduce the concept of material reuse, which is becoming more of a common task that we would be involved with as engineering geologists. So without further ado, I'll go just quickly into the outline, and really this sets out the framework, very basic framework of the talk, which is really into 4 sections. I'm going to talk initially about, and really the first 2 are more of a reminder, I would hope, about how naturally occurring soils might be used in civil engineering. And I put the term soil in there because the presentation talk title is in fact materials. Given it's a soils theme, we're going to focus on soils. So how these soils are used in civil engineering, we'll then look at the soil types and importantly how they relate to different landforms. Thirdly, we'll look at how we might evaluate the landform to infer a soil type and the distribution of those soils. And then also how we might, lastly, how we incorporate the landforms into the engineering geological model to infer what we're looking at, which is in this case material reuse, or the potential for reusing material. So really there's a couple of aims that I hope some people can take out of this talk. One of which is the role of geomorphology in engineering geology. I also would like a take-home message to be this terrain, or introduce and maybe talk a bit more about the applications of terrain evaluation and how that might be used to infer soil type and distribution. And also it would be good if I'm going to present some methodology about how those findings might be presented. So the 3 aims really of the talk, and I would hope that some of these come out in the talk. You'll see this reproduced for all the 4 different sections, and I intentionally bring it up because it's essentially hopefully taking you on a bit of a journey about how you might think about a project and how you might understand the distribution of soils and types of soils. So first section here, how do naturally occurring soils, how they're used in civil engineering. So really, material reuse is entirely dependent on the end use requirement. So and this varies, of course, with project to project and by structure. Really, it's important to get an understanding of this early in a project, to understand what exactly the requirements are, or what's the criteria for your project. So some of these dependents for material reuse include, I've listed them there: size, shape, particle strength, durability. Surface properties play an important role, particularly for wearing courses of roads. The strength and stiffness of a soil, the grading, its plasticity, and also aggressiveness of a soil. On the right-hand side, you'll see a series of essentially what's broken up into two groups. The upper two rows look at a construction material, which would be a crushed rock or broken stone or cut stone, which is essentially material sourced from rock. If we look at the cut or broken stone, think of things like dimension stone, breakwater armor stone, riprap. Essentially, this is the usage is to protect. And normally they're sourced from ripped or blasted, fresh, hard, and very durable rock. Also may require some screening to remove oversize or to make uniform. This other field of construction material, crushed rock, concrete, think of in use with concrete aggregates, mostly surface aggregates. Railway ballast is another one. Macadam pavements. We'll go into that a little bit more in detail later. Gabion stone road bases, sub-base, base courses, and drainage layers. So essentially these come from both weathered and fresh rock, and they also may have some of the criteria required for the cut broken stone, such as strength, durability, etc. The point here is that both of these are quite process intensive in that they do require or are related to a cost involved in processing that material, both in extracting, but also in preparing it for use. So really what we're going to talk about today are the bottom two rows, which are soils, and they're really broken up into sands and gravels, which are quite specialized and really quite rare to occur naturally in the environment. These might be used for concrete or mortar sand, pipe bedding, so think clean sands, likewise sand filters, and washed gravel aggregates as well. So these can be typically transported soils, alluvial, colluvial, aeolian soils, or windblown. And again, I just wanted to put that in there, that most of these sources have been exhausted, certainly close to capital cities, and they're quite rare to occur within 50 or 100k of most capital cities. This last group, which is quite broad and it covers quite a range of material types, these soils can be used for bricks, tile, clays, road bases. They can be stabilized, common fill, or another term is bulk fill, getting up to select or sub-ballast capping. We're going to talk quite a bit about these bottom three in this talk, but these are normally are either residual or transported soils, and includes also weathered rock. And ideally, there's no processing required of these soils. But sometimes they do require minor screening or processing, blending, etc. Stabilization of these soils is actually very common, particularly when there's nothing else available for your project. So some of the soil uses, well, they're really countless, but if I can break it up into three groups, really we've got embankments, and when I think of embankments, I think of essentially corridor projects, roads, railway lines, pipelines. This is where we have this the common and bulk fill, or common and bulk fill. These are synonymous terms. And then getting up towards the top of the embankments, we have more select fills for pavements and underlying the pavements as well. Rock fills are also used in embankments. Earth rock fill dams, think clay core, sand filters, earth fill, and also rock fill and rock protection. These first two are, well, in fact, all of these materials are quite specific and are quite tight on the criteria, and are unlikely to occur naturally in certainly the soils in close proximity to your dam site. So they're normally processed or won from rock and processed or imported. And then finally, there's all the other general fills, which might include airports. pile pads, etc. And really they offer the bulk and select fill would be used for these types of projects. And I put this down the bottom to show that both temporary and permanent works are considered in soil usage as well, both equally as important. So really the focus of today's talk is going to be on these embankments, or at least this is where I'm going to apply this terrain evaluation to embankments, given that terrain evaluation is very applicable to these types of projects, these corridor projects, where the terrain, we have quite varied terrain. So let's have a bit of a closer look at these embankments and what constitutes an embankment. If we take this railway embankment here as an example, we have our foundation, of course, or just by the way, this was the only decent image I could find, and this is stabilized sand around these culverts. So just maybe just ignore that stayed sand for a moment. And you can kind of see the different layers in the embankment here, where we have this common or bulk fill making up 2/3 of the embankment. And as we get higher up, we get progressively better quality. We come into this select fill zone, or it's sometimes called transition zone, to transition out of this lower quality material into what normally caps embankments. And in this case, we have a subballast capping on which you can see sleep is already laid, and then you put your ballast on top of that. So the general premise is that your more inferior materials do occur down the bottom, and it progressively gets better quality materials as you go up. And better quality, I mean higher strength and stiffness soils, and normally soils or processed rock. Some of the inferior fills can be encapsulated in the embankment. This does require a certain embankment height, though, to encapsulate your materials, and think of sensitive clays, or clays that react poorly to changes in moisture. That is, they will change volume and or lose strength with moisture changes. So the idea here is to keep these materials at a constant moisture level, and therefore they don't react. So that's the general principle, as generally becoming progressively more select and better towards the top of the embankment. The common and bulk fill, it's generally always sourced from cuts, and particularly in the corridor projects, whereby the earthworks is trying to establish a balance of cut and fill. So whatever you cut out of or extract out of a cutting, you will use an adjacent fills. This is an example of such material where you can see very bony, very much a rock fill, and really we're not going to cover this today, but this is an example of what might come out of a cut, and this would be located in the lower parts of the embankment. So this shot's a reasonably good one to illustrate that idea of we can see a cut up here and another cut that I'm standing on, and we can see the cut material that's been laid out progressively, and in reasonably thick layers as well. And this is a big difference between using a rock fill and or a soil one from Burrow. So here we have these cuts being laid out, but off in the distance here on the left, we can see an area that's been cleared of vegetation, stripped of topsoil, and it's being prepared and ready to win material, in this case colluvial soil, from this Burrow area. These are termed Burrow areas. I'm sure there are other names for them, but it's very common that these will be located in very close proximity to your alignment or corridor, and these materials will be used to cap, to form the capping of this embankment up towards the top, the transition zone, to transition out of this reasonably dirty rock fill into a more select fill. This is commonly referred to dump and doze in through here, and this also can be dumped or picked up and put into dozers, into dump trucks rather, and spread out across, or use of scraper fleets as well. So the important point here is that these are naturally occurring materials that are very close to the alignment that are used in this upper part of the embankment. This example of a pretty poor abutment, railway abutment, this was flood damage in this particular example, but the point of this is to show the layering, where down the bottom we have a bulk fill, or probably sourced from cuttings, and then at the base of this this abutment here in wing wall, we have more select fill, which is a more controlled, more readily controlled and material, and able to be tested as well. So just a little bit closer up under that that abutment footing, you can see the select fill above this quite nasty looking rock fill. This particular bridge, by the way, was actually removed. They couldn't do much for that. So we now looking at getting into what constitutes the select and pavement soils, and I use the term they're low cost for a good reason, and that is you clearly don't want to spend money where you don't need to. So finding these naturally occurring soils that require minimal or no processing in order to use in your embankment as your select and pavement materials is obviously ideal, and that's the lowest cost. So natural soils gain their strength from one or a combination of these four principal mechanisms here. If we just start with the mechanical interlock, a couple of things with this: the very angular grains, they rely on friction, interparticle friction. And you can see the scale here of 50 mil, up to 50 mil. So really these are a little bit rare in nature to find naturally occurring soils that are I don't want to use the term sorted, but they're certainly eroded and deposited in these in this grading, which we'll talk about grading in a sec. Well, actually, we can look at that now. So this is what I would regard as a poorly graded gravel, and if we look over at this grading particle size distribution curve, this is the equivalent here, which is a macadam gravel, which is essentially a gravel with very few fines. So you can see there's not a lot of sand, not a lot of fine grained material, and it's mostly in this gravel size here. So, and this was introduced in the 18th century, and this is how they used to sheet their roads, with this type of material. Not great for sealing the roads, but certainly it was used, and dare I say would have provided a reasonably bumpy pavement to drag your horse and cart along. But anyway, this is a good source of strength for naturally occurring road gravels. Self-cementation as well. So calcium carbonate soils can generate this self-cementing property, which can give it strength, and also again down at the clay size particles, you can get these negative pore pressures as well, which act as soil suction effectively. So you can gain some strength from that. So we come to this last group, I guess, of this dense packing principle. Now this has a few terms. Dense packing is one, which essentially what that means is a well-graded gravel, in this case, whereby you have a wide range of particle sizes from coarse to fine. Ideally, you'd have a few fines to also bind things together and get a type of this effect. And if we look at a densely packed product, or densely graded or well graded, really that's what they are well graded gravels. We'll take this example here from McNally to show this curve here, showing a broad range of particle sizes are represented from gravel through sand down to some fines, although not many, less than 10 or so microns, 50 microns. This particular grading curve is from a fresh crushed rock, so it's an artificially produced material, but it gives you an idea of what a good dense product might look like. If we look at what it looks like on a compaction curve with moisture down on the x-axis and its dry density on the y, we can see here we have these GW, which is a well-graded gravel, producing the densest product. If we compare that to these well-graded sands coming through to silt, and then down at your clay-sized or clay soils, high plastic, low plastic clays. So these not only can hold a fair amount of water, they produce a product or a soil with a lower dry density than your granular soil. So really the ideal soil of all of these, it has all of these properties, but ideally we're after these well-graded gravels are definitely ideal, and where they occur naturally, that's the target for your select. Most other soils that you'll encounter along a project, you can almost always use in the embankment for the lower part in your bulk or common fill. It's really what costs a lot and what is rare to find are these select or pavement materials. So really that should be a challenge and an aim of an investigation to try and identify these soils that require low processing and hopefully no stabilization. So if we look at what a naturally occurring well-graded sandy gravel with some fines might look like, well, this would be considered, certainly in my book, as a type example of such material. Here we're in the Pilbara region of Western Australia. We have a pisolite source, which is an iron deposit source very close by. And we have this accumulation of an area at the bottom of this, so the colluvial gravel, which is accumulating these gravels that are eroding off this from the source. And in this instance, we have a borate area that's been identified as being suitable, and it's been ripped and conditioned with moisture in preparation for use in a railway embankment. So that's an example of an ideal naturally occurring material. That's what it looks like when it gets laid down, compacted in as a capping for a railway line, and it's being tested in this example. But it goes down like concrete, and it's an extremely good and arguably some of the best naturally occurring materials you will find anywhere. Here again, we have another borate area with a similar material, a sandy gravel with some fines, in this case clay. Close to source, a slightly different source rock in this instance, but nonetheless close to source, accumulated, and you can see a pretty uniform soil. There's not a lot of layering or otherwise in this soil. It's quite uniform. And here we can see it's been loaded out for use in an embankment, and this certainly is a select fill that is protected and used selectively. If you're lucky enough, you can have, in this instance, 4 meters of a nice naturally occurring gravel accumulation. So we can see the boundary here with the underlying rock, and here we have 4 meters of a uniformly distributed soil close to its source. So here, it's probably a little bit more angular and larger, up to probably cobble size here compared to those other two, but it's still a very, very good product, naturally occurring product that was used for developing the select zones in embankments. You also will find, if you're allowed to dig holes when you're out field mapping, you'll often encounter soils like this, and a good thing to do is to, if you're able to have a look at those materials and assess whether or not they'll be suitable. In this case, this is a good example of in this case, a finer sandy gravel, and you can tell that it's a little bit further from the source, being these clasts or little particles are quite rounded compared to the other ones that we were showing. But this is still a very, very good product, naturally occurring product that would make a very good select fill. And this is again something you might expect to encounter near the surface or at the surface when you're during field mapping. So to sum up the section, really the ideal select pavement or soil for a low cost construction is going to be easily excavated with conventional earth moving machinery, not sensitive to change in moisture, that is sensitive to volume change and loss of strength. It will be well graded or densely graded, strong, durable individual particles, have a high strength and stiffness when compacted, not require no processing, like crush screening, etc. Close to the source, so short haul distances, and I talk about cost. There's also environmental costs. So ideally, you'd have a borrow area that's easily rehabilitated. So in summary, or to say what that product is, it's essentially a naturally occurring, they are naturally occurring granular colluvial soils. And here's an example of a completed embankment, railway embankment, whereby you'll have sleepers come on top of this and be placed. So this is a sub-ballast capping, and again, it's some of the best naturally occurring materials you'll have or you can find. And this is not processed at all. It's just one from borrow, moisture conditioned and compacted in place. Where you don't have this luxury though of a naturally occurring material that you can use, very commonly you have to win from a rock source. Here is an example of a basalt that we used very close to where we needed to use it. Mostly fresh, a little bit of a few weathered areas here and there, but mostly a fresh rock. Going through a processing sequence of jaw and cone crusher, and you can see where the material, what it looks like going in and what it looks like coming out. So this is that crushed rock grading curve that we saw before. This would match that curve, and this is a sub 20 millimeter product where we have a good distribution of particle sizes from sub 20 down to some fines. So this would be regarded as densely graded base sub 20 or DGB 20. And what that would look like with a bit of moisture, in this case in a lab where we compacted it in a mold and extracted it from the mold. So very good particle, very good properties for this material. Just going back here, you can see too, we've got quite angular particles, so providing quite good friction, interparticle friction between those individual clasts. But the issue with this is expensive. It costs money and time to produce this sort of material. And very commonly, you'll also have to stabilize using lime or cement or some other stabilizer to produce a product or a soil or a material that is going to be suitable for use in your project. Okay, so now we've looked at how these soils are used in civil engineering. What we now need to do is I want to introduce this theme of soil types and how they relate to different landforms. So, I mean, I don't want to spend time on this because we should all really be aware of these, but the different soil groups really are fine-grained soils, coarse-grained soils, and organic soils. And really, the way I think about this is they comprise of these survival assemblages from either rock fragments as minerals from the parent material, plus any new minerals that form during any chemical change once it's been deposited. So we have really two groups here in situ with residual organic laterites and jury crusts. Arguably these form rocks, but they're in this category as forming in situ. And then we have the other group, which is transported by wind, ice, gravity or water, aeolian, slope wash. This is what I refer to as these colluvial gravels or colluvial materials, rather, soils that really are derived by gravity and maybe a bit of fluvial activity as well, but chiefly gravity. Glacial, alluvial, estuarine, of course, marine, and lacustrine or lake deposits. And I'm more and more becoming or encountering anthropogenic soils as well, and really that just means all form or manner of fills that you will find in most projects. Certainly in and around capital cities, you'll often encounter existing fills from hundreds of years or more recent periods, and they also can comprise crust rock from cut or from burrow. In this particular example is a sandstone one from as a tunnel spoil one in Sydney here, where we have a fair bit of tunnelling going on. So this is a way that we're able to use these reasonably good quality sandstones when they're excavated from road-headed tunnels. So a few things that do influence the availability of a soil for transportation or otherwise, or just the development in situ, is climate. And really, we've got a few climates here, and I wanted to put this in here because it is hopefully an international audience, and some of you might be represented by the dry or cold environments, and others in temperate and tropical. So I think it's worth considering here that the climate plays a reasonable part in the ability or availability of soils for transportation. So we have these cold and dry or semi-desert arid environments where we have slower weathering, less organic growth, and less accumulation of organic material, less leaching of mobile constituents as well. And really, there's not a lot of soil. As far as the climate is concerned, the soil development is not, it doesn't produce a lot of soil to mobilize for transportation. Whereas if we look at the increased rainfall and temperature, such as in the temperate and tropical environments or climates, we have deeper and faster rates of weathering, and essentially means that there's more material that can be potentially be mobilized. And then that feeds into this this field or this concept of these morphoclimatic regions. And essentially what this means is that each region has a climatically induced process or processes, plural, involving both weathering and erosion. And why these are important is because they do give rise to these what we call all these characteristic assemblages of landform and soils as well. And this soil development not only depends on the climate, which we've just looked at, but also the intensity of weathering, the tectonics of that particular location, the original rock composition, and also time. And you'll note down here that there's this azonal term that's used, and really what that means, or the rest of them are basically termed zonal, which is landforms that only really occur in certain morphoclimatic regions. So think of these, these equatorial regions here, and you'll get a certain type of landform that really only occurs in these equatorial regions. You just won't get them in the desert areas, as an example. These azonal morphoclimatic regions are the landforms that are found in a variety of the morphoclimatic regions due to their association with particular structures or rock types. And really what that means, if you look at the Andes that run up the spine of South America, they're really independent of the climatic influences and cover this area over many climatic zones in response to the tectonism that's occurring. Likewise, the Rockies, and there are other examples up in the Himalayas as well. So these are an important concept to understand, and the next slide just shows how we can link those morphoclimatic regions to characteristic weathering rates and surface processes as well. And that's important. So we want to try and get this link to these morphoclimatic regions and surface processes. So I've left that there if you want to pause this later and have a read. but really it just talks about the geomorphological processes in this column here. So here are all our different morphoclimatic zones. These are the geomorphological processes, and then here we've got some potential geohazards or design considerations included. So look, Fuchs presents in these schematics or these 3D models in his book, and I encourage you to go and have a look at these in detail. You're certainly not going to get the detail from this one slide, but what this tries to do is link these morphoclimatic zones to these what are typical or I guess characteristic surface processes and soil occurrence. So if we just take a couple of these as an example, if we look at the temperate or semi-arid morphoclimatic zone, we, essentially this has, it's dominated by alluvial and colluvial systems, and they generate relatively thin soils, both granular and fine grained. And there's some more detail in here about the different landforms and whatnot that you might encounter. Looking at these desert environments, really, when I think of these environments, we think of, these relic surfaces, these plateaus, alluvial and wind-blown transportation of soils, slow residual development of dewey crusts by upward leaching. Up to these wet tropical areas, we have characteristically deep and fast rates of chemical and physical weathering, reactive soils, etc. Down here with the glacial, or actually looking at the periglacial, where we have complex physical weathering, frost action, probably limited fluvial activity or transportation. It's mostly down to the physical effects of the freeze-thaw process. And then finally, these glacial or mountainous morphoclimatic terrains where we do get a high rate of physical erosion, high transportation and accumulation of these mostly granular soils. These are particularly complex systems and produce very complex landforms and soils just due to that constant cycle of glaciation. And they're normally associated with the higher tectonic regions or zones as well. Loess is another finer soil that's associated with this sort of morphoclimatic terrain. And of course, till is the main deposit from the glacial action, which is a particularly nasty material from an engineering perspective to deal with, not only to investigate and characterize, but to build in as well. And just a word of caution that while these are the present day morphoclimatic terrains, an area that you are currently in may not reflect its current morphoclimatic region. In other words, particularly for the older terrains in low tectonic or intraplate tectonic settings, it might have gone through a series of these morphoclimatic terrains and have soils that are preserved from previous regions. So that's something to keep in mind. So really, we're going to try and link these landforms and surface processes to soil distribution, and really this is what geomorphology is, which, if we look at the definition of geomorphology, the study of the Earth's surface, it's landforms, processes, and characteristics, which is essentially what we've just been talking about. Back in the 60s, the so-called hypothetical 9-unit slope model was introduced, and it's been reinvigorated recently by several people. I cite Fuchs down here, who talks about it in the paper. So again, encourage you to go and have a look at that paper. But look, essentially what this is trying to do is to associate each landform with a particular slope process and therefore soil type and distribution. And when I think of this, I think of the soil makeup for this hypothetical system in the form of energy. So higher energies for your coarser or granular soils, and lower energy in your finer grained soils as well. So if we take a look at this hypothetical model here. We have this, this interfluve or upper slope where we have not a lot of slope angle and quite a bit of residual soil development. So not a lot of energy to mobilize the soils. So a lot of residual soils develop up here. When we come to this transported or the steeper face, we start to get what's called this full face. And just take these with a grain of salt, these angles, because really this is just a hypothetical model, and as you will see in a few slides, how we apply that to other areas that may or may not have all of these elements combined. Anyway, so we're at this free fall face, and then we're proximal to that face, where we get these colluvial foot slopes, and as you can imagine, coarser soils. And as we become distal to that face or source, we get the finer transported soils that develop and get deposited further away from that slope, and then eventually ends up in the actual alluvial channel itself. So the point of this here is to recognise each landform is associated with a particular slope process and soil type. So if we take an alluvial fan as an example of a part of that of the slope process, beginning up here and ending down here in this case a braided river system. So if we look at this alluvial fan, first of all, it's large. It's many kilometres across. And it extends several kilometres out from its source. And when we think about this, not only can we see its shape, and by the way, I did choose alluvial fans mainly because they're very obvious, and it's a good way to illustrate these points. And this is the other term that I want to start. I'm intentionally using is this, try to understand soil type by its association with these different landforms. So look, we've got an alluvial fan here, and if we look at the distribution of that fan, similar principle. If I go back here to this, we're essentially down in this part of this hypothetical slope model, whereby we get coarser proximal and finer distal from the source. This being the source here, and this from Fuchs, we see an upper fan, a mid fan, and then down to a distal and fluvial, and we get these the different types of soils from what's a gravel up near the source, down to mixture of sand and gravel, and then finally down here it uses the term mud. I'm not particularly keen on the term mud, but anyway, finer soils distal from that source. So again, we can use this model and our understanding of how these alluvial fans develop and the distribution or the extent of that alluvial fan to try and understand what these soils might look like over this area. Fluvial systems, I put these two up here. The left-hand side's a braided river plain, and the right-hand side is a meandering river, different energy levels, higher energy, lower energy on the right. So again, it's a fundamental in this process is to understand how these soils are forming and the types of soils that you might encounter. And it can get quite complex. Certainly the examples I showed earlier were not as complex as this. And so these do offer some of the more challenging soils to characterize and differentiate, and particularly with its extent. So we do get a mixed bag of soils here. But again, so really the point of this slide here is that it requires what we are trying to do here with this association. It requires an understanding of sedimentology, essentially, which I expect most engineering geologists should have a reasonable handle on. All right, so we've covered off how a soil might relate to a particular landform. Now we want to look into, well, how do we actually evaluate, or what are some of the techniques that we can use to evaluate the landforms to begin to break it down and infer these different soil types and how they're distributed. So how we do that? Well, we use this this concept of terrain evaluation. And I wanted to open by just saying that Griffiths has I would think an extremely good paper on terrain evaluation, and by that it's a very comprehensive look back at where terrain evaluation has come from and where we are as of 2017. So it's a really good paper to go and have a look at, and it certainly describes terrain evaluation in more detail and probably better than I'm about to explain. Nonetheless, there it is there. So terrain evaluation. I've got two basic definitions here. And apologies, I am going to read this, but terrain evaluation, and quite deliberately, for engineering utilizes a suite of techniques to assess ground conditions that can assist in organizing, that's a key word, and communicating ground information. Now that's not mine, that's paraphrasing from Fuchs and Lee, but essentially that's a more formal definition. And this is really mine. I think a terrain evaluation is recognizing landform patterns and surface processes, which is basically geomorphology, and assigning characteristic geotechnical properties based on either association with that landform and how it came to be, or actual data, or hopefully both. So I put this as an example on the right-hand side of a terrain model from Griffiths, where he shows that what's a conceptual understanding of the landforms and how they might relate to the engineering problem. In this case, he's looking at the dip of the rock and how that might relate to stability. For soils, we might look at some of these other soil terrains and how they might reflect the soil type and reuse potential. So again, this is what I would consider a conceptual understanding with these block diagrams, and this bottom left is what would be considered an observational way to present those different terrains, which is essentially what you have interpreted as your terrains that you've come up with. So observational and conceptual. So terrain evaluation, there's a few techniques that can be used. Geomorphological mapping, geological mapping, engineering geological mapping, remote sensing, and then this fifth one called terrain classification. So terrain evaluation includes all of these 5 items. What I would like to, and I would like to focus on this terrain classification, which is a key part of this terrain evaluation process. And the reason being is that I think it's I would like to show you how this can be used to infer soil reuse, but also because most of us should be quite familiar with these, certainly the first 3 points. So terrain classification, I've got a more formal definition that they're based on the principles. Not, in fact, apologies here, but I wanted to open with this, that terrain classification is in fact based on the principles of geomorphology. And I have actually extracted I think these might be a bit wrong, these links to the reference. But anyway, look, geomorphology is a study of the classification, description, nature, origin, and development of landforms, and how they relate to the underlying structure and history of geological change. Terrain classification is a way of summarizing the physical aspects of a landscape through this form of classification. In fact, that is from modified from Lawrence. So that's the way that he describes it. It's a way of summarizing the physical aspects of a landscape through classification. And really, this is my definition of terrain classification, is recognizing, very, very simply, it's recognizing patterns and the different slope processes that are occurring for your particular landform. And for soils, really the key is to identify these landforms and processes, and that's the key to understanding the soil type and their extent. So this is what terrain classifications are very useful to identify landforms and soils. So terrain classification is broken or subdivided into 3 aspects of the landscape. It divides the landscape into 3 components, starting from what's termed land systems, which would be the broad. If we look at this example here, which this is around 70 kilometers across, we have a circle showing within this there are many land systems that are going on. So you would evaluate the terrain at this scale, essentially, down to what's termed land facets. That's this purple circle. You would assess it at that scale, and then finally, at the most detailed level, you would look at these things which are termed land elements. The key for terrain classification is that it can be evaluated at scales that are relevant for engineering projects. So at this scale here, you might think, well, that's not going to be much helpful for an embankment or a road that I'm going to put in through here, whereas the land facet and land element scale, it certainly is going to be applicable. So you can develop these that are at scales that are relevant to your structure. So we're going to discuss, just quickly introduce these 3 and talk a bit more detailed about them. So these land systems, the definition of this land system is really they're landforms with contiguous recurring patterns of soils, of vegetation, geology, and then of hydrogeology and hydrology. And they're generally assessed at reasonably small scales, so normally at 1 to 100,000 or even smaller. In this example here, which is in a tropical setting, where we have these squares which are 2 by 2 or 4 square kilometers, and I think this, from memory, this is a 1 to 40,000 scale. We have this area divided up into these different land systems. So you can see around the outside, we have these alluvial processes that are occurring. We have some structurally controlled ground in here. We have some landslide controlled landforms in here, and then this is continued over this area. So we've broken up this area at a reasonably small scale into these different groups of landforms with these contiguous recurring patterns. These are not particularly useful at the scales that we need, but nonetheless, it's a good starting point to begin with. So I'm probably going to have to keep moving along quite fast here because I'm not going as quick as I thought I would. So coming into these land systems here, this is the northern part of India, the border near Pakistan, where we can see that there's a few things going on with the Tibetan Plateau up here. So this would be one land system. These foot slopes down the bottom would constitute another land system where we have different processes going on. And then finally down the bottom here where we have these alluvial plains. So this is the scale that you would assess these land systems at. The next level of detail are these land facets that are established at around the 1 to 10,000 to up to 100,000 scale. And these are these contiguous terrain units of uniform slope and parent material against soils and hydrogeological conditions. And the key here is that they're sufficiently homogeneous to be considered uniform for most engineering purposes. These are the building blocks for these for land systems, and they're typically named after the landform that they comprise. So if we look at the same example that I had up before, we can see we've got a lot more detail now, and we've broken up into different terrain or land facets. Like you can see landslide here, these what we call triangular facets here, and alluvium down the bottom, just in more detail. And the final level that we look at is these land elements, which are the smallest units, and they really look at these geomorphological attributes, which you can see over here. So gullies, changes in slope angles, etc. And they really follow these symbols. Everyone should be familiar with these symbols, but really they're not standardized, and they in this case I follow Woodland 1971, which is pretty much the standard that the go-to with all the different symbols you can use. So what might this look like? Here we have a a map at a 1 to 10,000. So here we have 500 by 500 grids showing the distribution of these land facets, all of these different colors and codes relate to a different land facet, and then superimposed on that are the land elements, which are these. In this case, we can see some headscarps for landslides, some ridges, etc. And this is getting now quite applicable to at an engineering scale. So what are some of the tools that we might use to evaluate this terrain? Well, really, ultimately, this is very difficult to do without a geographical information system. I've used Esri or ArcGIS for about 20 years now, but I am starting to get into QGIS, which is great. Also, Global Mapper is another one that you can use. So this just collates all the spatial data that you might have available. And it's really important to collate all of the as much spatial data as you can get your hands on. Another key component are these digital elevation models, which without it becomes very difficult to do evaluate the terrain at a scale that's suitable for your project. Also, what's quite important is previous land use. Here is an example of a historical photo showing what we're encountering now on a project, and here shows what fill they used, and it gives a good idea of what the materials that you might find in your present day project where you want to build in or extract these fills. So this is also an important aspect of building this terrain evaluation. So I just want to touch quickly on DEMs, or digital elevation models, and vegetation. If I look at the image on the right from the Pilbara region of Western Australia, so very arid region, low rainfall, low vegetation growth, etc., versus the one on the left, which is a tropical environment where really I've got no idea what's going on with these landforms. So if we start looking at this here, we essentially don't need a DEM to break up this into different patterns and try and understand what soil types and distribution might be like. Here we have have the source material, number one. Number two is this the transported soil coming off or in close proximity to the source. Three, we have a different pattern here. It could be rock at or near surface. And then we have some more soil here, 4, and then the alluvial channel that's separating. So at a really fundamental level, without vegetation, you're able to actually read the ground and start to understand the patterns very well. Over here, I certainly can't go to this level of detail. So where do we get the LiDAR, the DEMs from? There's a couple of sources. If you're lucky enough, we can get LiDAR 1 to 2 meter DEMs derived by light detection and ranging. And this is one project we were looking at in a tropical region here, where we had LiDAR on this side, and then on this side we had nothing. So we got some 12 meter DEM, a 12 meter DEM by satellite, and you can see the quality is really not sufficient to evaluate the terrain at the level of detail that we can do on this with LiDAR. So LiDAR is a really vital part of this process. Here is the same project whereby we have a square which is about 600 meters by 600 meters. If we look at that without just from an aerial photo, that's what we see. So really, I can't tell what's going on there at all. But if we look at the same area and the LiDAR with the same scale, these are the same photos, one with aerial, one without, and showing the LiDAR, you can see the level of detail we can see from this light detection and ranging, which essentially looks through the trees to give you a terrain model. So we can see a well-formed headscarp in this case, a landslide headscarp, and some deposits that have been progressively downcut through. So this is really the compilation of a terrain evaluation from both point and line data, and also these DEMs that we hopefully are able to get our hands on, where we might have we start to compile the geology, the point data, your hill shade model from the DEM, some slope aspects, slope angle. Obviously contours are easily generated. Some hydrology, very important part is the hydrology. And this enables us to understand these land systems. and then in more detail, these land facets and the distribution of soils and rock types. And then I haven't got an example here for this particular series, but land elements had, again, a larger scale than this. So just a quick one on a couple of slides on how we might present some of the outputs. Really, there's only a few ways. One is a suite of these so-called thematic maps, which is the observational approach here, whereby we put all our observations at a, in this case, a scale of, I think from memory, 1 to 7,000, actually 1 to 10,000, where we have our land elements and land facets shown and other geomorphological symbols shown. Another way is by block diagrams, which are going back to this more conceptual method of portraying these landforms and systems or processes. The other one is the 2D conceptual, and I pulled this up here to say these need not be particularly complex or pretty, I guess. In fact, I encourage everyone to start here and draw up these conceptual ideas of how your soils might be distributed. And by the way, this looks remarkably similar to that 9-unit landscape that we had up before, or that hypothetical 9-unit landscape, just showing the distribution of soils across that slope. And this is the same, this is that same model, and just in more detail, where we start to really break it down and describe these different soils that might occur as we go down through that slope. Again, another very rough one that I've used in a meeting, which was a really good way to articulate where we might find good or most suitable gravels for borrow for a project, and where we might find poorer ground or poorer soils that are not particularly suitable. It can actually get a little bit more complex here with quite a bit of detail. This was for a tunnel project where we were trying to show conceptually the distribution of soils for an entry-exit point to a tunnel. And again, this one shows the distribution of soils for a railway cutting. So we're on the home stretch now, and I really want to pull all of everything that we've discussed on the landforms into this into an engineering geological model, and how we might infer potential reuse. So just a quick recap, we worked out what soils we need, we reviewed the soil formation and how they're associated with our different landforms. We've classified our site into separate terrains based on the geomorphology and geology, and now we need to link that to our project requirements. So this is the engineering geological model, and I've pulled up this reference here for Perry et al. 2014, which really described the engineering geological model in a lot of detail. But essentially our terrain evaluation has completed stage 1 here, whereby we establish the big picture, we identify the main issues, and we divide the ground into regions with similar engineering characteristics, or these engineering geological units. So the aim for reuse, our aim to inform soil reuse, is that we want to group and simplify. We want to describe the common characteristics of these different groups that we've put together. Translate these group descriptions into geotechnical data for engineering design. Identify the potential resources. Outline geotechnical constraints and of course inform investigations. And I put that project stage matters there because really this can be applied to any project stage, from conceptual pre-feasibility through to feasibility, or even and certainly design stage, prelim and detailed design. So on that different project stage theme, on the right hand side you can see we've in this case we've established our terrains via this remote sensing exercise, and then we've gone and validated that in the field using, in this case, a helicopter to fly over and make notes about these different terrains, and then we can come back in the office and adjust accordingly, both the boundaries and also the descriptions. Another good way, normally at a more detailed project stage, is to verify via mapping, and you can see here we've got a track log of where we've been. We've got the design in the background, we've got some photograph locations, and then we've also got these lines with attributes, which you can't see the attributes, but the lines that refer to the boundaries, and we can use these to guide defining those different terrain boundaries or terrain facets. So mapping's a vital part. And then the more detailed stage, we might have in this case, a series of colluvial gravels that we've identified and a potential borrow area that have had test pits dug through them. So this would be, you know, in the detailed design or maybe preliminary design stage. So if we can just look at this pre-feasibility stage, which arguably this whole process is most suited to this pre-feasibility stage, a way that we can show our potential reuse is first of all to identify or to show our identified soil types along our corridor. So you can see here, these are the soil names that are identified from the terrain classification. This is the genesis of those soils, so how they were formed, and then we can also describe the soil characteristics. Next, we might want to group these into soils that display similar physical characteristics, which we term these engineering geological units or domains. And you can see here for these alluvial soils, we've got these 3 different terrain units that we have lumped into this one domain here with a particular engineering geological description and any geotechnical constraints. We can also use GIS to quantify that domain coverage over an area. Here we have our geological unit, our engineering domain, and basically our percentage of that corridor that domain represents. So this can be used for pricing of a project. Here's an example of the same example, but one here we're showing the soil types, and down the bottom we show the domain, the soil domain that's applicable. Here we have a colluvial gravel, which we've linked to a very good suitability, or a domain with good suitability for soil reuse. So, and here, this is a way that we can show this potential for reuse. And again, we're based on association with its landform. So we know that these fine alluvial soils are probably not going to be particularly good for, certainly not for our pavement materials, but they may be quite suitable for the inferior embankments. Whereas our colluvial soils have got a high potential for reuse, and they form the most suitable source of embankment material. You might also want to identify any constraints for reuse, such as oversize, grading issues, strength, behaviour issues, etc. And again, this can be based on association with its landform or process or experience with similar soils. Another good way to articulate these ideas of these different terrains is these terrain summary sheets, whereby again, it's simply describing the geological, well, first of all, identifying the terrain and then describing the geological characteristics, and then also assigning geotechnical characteristics to that domain. Here we have an alluvial fan that we've identified and then described both in geological and geotechnical terms. So here's another example of a coastal swamp material that we've also looked at and made a specific comment on material reuse or borrow potential. You can imagine a coastal swamp's not going to be particularly good for reuse. And I've only got a couple of slides left, but really an important factor, and I've only got one slide on this, but a really important factor is data, of course, crucial for design stage. And really this separates the general or bulk fill from the select material. And it's really important that, that you do group and present the data in against the different terrains or engineering geological units that you've come up with. And these are also used, this data can also be used to verify the boundaries as well as the inferred characteristics. And you can adjust those boundaries and characteristics accordingly as well. Another very reasonably high level or basic way to look at reuse, how you might display that reuse a potential really basically by denoting an S for suitable and an U for unsuitable for your different materials or domains. And then along here are all the different materials that you might want to use that for your project. So it can be as simple as that, with a few disclaimers down the bottom here. I think we get up to 19 odd notes, but another way is to, this is for broad suitability, but also these borrow pit management plans are useful. So look, really some closing thoughts is that geomorphology, or the closing thoughts on geomorphology and terrain evaluation is that they really are an integral part of engineering geological models, particularly for corridor projects. They work well at almost all scales, but they're most useful in the early stages of a project. And they're used successfully to infer reuse potential of soils, but also that technique, or the techniques that I've shown, can be used to assess the reuse of rock from borrow or cuts, foundation conditions along a project, and to identify geohazards and geotechnical design considerations for your project. So a few references here and some good reading if you're that way inclined. And finally, thank you for giving me the opportunity to talk to you guys today, everyone. I don't have a Twitter handle, but here's a LinkedIn that you can use to contact me if so wish. Thank you very much.
Thank you. Thank you, Tim. That was an excellent presentation and too informative, I think. Due to that, we're a little bit over time. I think we can answer one question. There's one question from Tumaika Dachikocha. Thank you very much for your nice and detailed talk. How can we differentiate residual soil from transported soil in the field?
Well, that's a very good question. Again, I would link or come back to where you are in that landform. So by understanding what landforms your investigation point is at, that's going to give you or give away what you might expect with respect to a transported or residual. You can get some transported soils that are very similar to residual soils in the way that they look and the way they behave and the way that they're classified. So using the examples that I gave today, I think assessing the terrain is going to be key in understanding if it's a residual or in situ versus transported soil.
Okay, so I see that there are like more questions. I think we should move to the next presentation from Sarah Bastin, and we can answer more questions in the end of her presentation. Thank you, Tim, once again. So now I would like to welcome our second presenter, our e-YEG presenter, which is Sarah Bastin. Sarah Bastin is an engineering geologist in Becca Ltd. Please, Sarah, if you can turn on your camera. She obtained her bachelor degree and PhD degree in geology from University of Canterbury. She worked as a postdoctoral research fellow with QuadCore in New Zealand Centre for Earthquake Resilience. Her main area of research has focused on relationships between geomorphology and observed distributions of liquefaction and evidence for paleoliquefaction. In her current role, Sarah has undertaken slope stability investigations, including 3D rockfall and debris fall modeling. And we have to mention that Sarah has been awarded as runner-up in 2018 Richard Walters Prize from IEYEG in San Francisco. So, Sarah, welcome. I'm sorry for taking a little bit of your time.
No, that's fine. Can you hear me?
Yeah, we can hear you. Can you turn on your camera? Is it okay?
It should be on.
Okay. Okay. Yeah, I
can
can
you
see
my
you now.
presentation?
Yeah, I can see your presentation.
Okay, great. Sounds like we're ready to go then.
Yeah. Okay.
So thank you for the introduction and thank you for the opportunity to present today. So my talk today focuses on, or it follows on a bit quite nicely from what Tim was just talking about in terms of geomorphology. And as an engineering geologist, we sort of have a unique skill set of taking our geological background and understanding landscapes and applying those to engineering problems and how we take this into design. So what I'm going to talk about today focuses on some of the work that I did as part of my PhD and as a postdoc research with QuakeCore, which is a centre for earthquake research based in New Zealand. So before I start, I wanted to go through what is liquefaction. For some of you, it might just represent a paragraph in a report where you feel obliged to put something in. Some of you might not have heard about it before, and for others who are from New Zealand, you might actually be very familiar with the topic. So when I talk about liquefaction, I'm talking for a start about the process. The process of liquefaction occurs, earthquake-induced liquefaction occurs as horizontal earthquake waves cause soil to densify. As those shear waves are coming through, the soil tries to move to a denser grain arrangement and squeezes the water out, resulting in increased pore water pressures. As that pore water pressure increases, it can exceed the confining pressures, resulting in a collapse of the soil skeleton and a loss of soil strength. As the soil transitions to this phase, we talk about it being liquefied. So we can assess the susceptibility of a soil to liquefaction based on in situ testing. Typically, soils that are susceptible to liquefaction are loose, unconsolidated and saturated fine sand, typically within 2 meters of the surface. Now, the geologist in me starts thinking, well, if I think about geomorphology and depositional settings, which settings are these likely to occur in? And how can we actually use this in our design? So if the way that this is often assessed is through in situ testing, as I mentioned before, typically through the CPT, which is an instrumented cone that is pushed into the ground under a defined load. And then we measure the resistance of the soil to that cone being pressed in. Typically, this is done either by a rig-mounted system, or you might even have a truck that can do it. These can apply different loads and measure resistance of the soil. So what can actually, well, why do we actually care about liquefaction for a start? So obviously the process by which liquefaction occurs results in the soil sort of behaving like a liquid. That soil can be ejected to the ground surface where we can have surface effects. These can include liquefaction ejector. So you can see that sort of in the top image here. You can have raised manholes due to the soil sort of pushing stuff up in the ground. And if you're close to a river, you can actually have your liquefied soil flowing towards the riverbank, or other free faces. So some sort of break and slope that enables the soil to flow sort of like a liquid. Obviously, this takes the ground with it, and you can get cracking in the ground surface. So nice little image here that shows the surface effects of liquefaction. And if we start thinking about the interactions with structures, we can start to see why we actually might start assessing liquefaction and thinking about the effects to infrastructure. So what does this actually look like on the ground? Typically, we have the surface sand blows, which you can start to see here along with surface flooding. Lateral spreading, as I mentioned before, where the ground surface is rafted towards the river, you often get big cracks opening up in the ground surface, or you might just get a lined crack with sand ejector at the surface. If you're lucky, you might even find these features in a vineyard, which means you get a nice excuse to go visit vineyards. So I've been oddly specific with my terminology of liquefaction. So the story for me started back in 2010 with the 2010 Darfield earthquake in Christchurch, New Zealand. So my hometown. Middle of the night, or about 4:30 a.m., we're woken up with strong shaking. And as daylight approached, people started to see sort of surface effects of surface flooding and sand volcanoes that had formed on the surface. The next few days, as a student at the time, was spent literally shoveling silt and sand from people's backyards. So we started to see the effects firsthand of what liquefaction had on these people, who in some cases, it simply meant they couldn't get their garage they couldn't get into their garage because of the ground surface had settled. To some people who had had their houses ripped in part due to lateral spreading towards the river. So following on from that, we can start to see, well, the image I was showing before of the nice cartoon showing all these severe surface effects actually happened in reality, where we've got lateral spreading Your bridge abutments had settled and narrowed, pushing your bridge deck up. So obviously you don't want to drive up that bridge anymore. You've got surface effects of liquefaction with raised petrol tanks, twisting of bridges. As we get the lateral spreading, the riverbanks narrow. So obviously the length of your bridge is no longer the length of your channel, so you get warping. And you can also get the riverbank popping up, reducing flow capacity, resulting in flooding hazards. So what does this actually look like on a map? So this is the city of Christchurch. You can sort of see in the background, overlain with the orange color is moderate to severe liquefaction, and then the yellow is minor liquefaction. Note the white is no liquefaction. It's not covering the whole region because what they've done here is they've plotted specific properties where they've been to visit and said there was no damage at this site. So outside of this region doesn't mean necessarily there was no damage observed. It's just where was actually covered. Now, to the trained eye, you might start to see a few features popping up. We've got a big braided river coming through here. Hopefully you can see my screen on the mouse, otherwise sorry, mouse on the screen, otherwise I'm going to be sort of pointing to nothing. And then through here, we've got a meandering river that comes right through the city. Now, obviously this caused a lot of damage within the city, as you saw in the previous image. But what happened next? We had the 22nd of February 2011 earthquake. The epicenter to this was within the Port Hills, which are located south of the city. So we had very high ground accelerations recorded within the city due to the close seismic source, and we had much more widespread liquefaction. So you can start to see again, so this is our central city through here, and we have towards the eastern suburbs a lot of liquefaction occurring. So the meandering river through here, another meandering river through here. So this now became part of what was termed the 2010 to 2011 Canterbury earthquake sequence. There's debate if this is an aftershock of the September earthquake or its own sort of part of earthquake clustering. We then had the June earthquake, in which there was two events spaced a couple of hours apart, magnitude 5.3 and magnitude 6 earthquake. Again, caused widespread liquefaction in eastern Christchurch. And then December 2011, magnitude 5.8 and 5.9, again, a couple of hours apart. And you can see similarities in the distribution of liquefaction across the city. All in all, there was about 10 episodes of liquefaction recorded in Christchurch. The damage resulting to these properties, we had about 7,000 homes or upwards of 7,000 homes that became red zoned. This essentially meant that repair of these properties was considered uneconomic or too disruptive to the landowners, and the government purchased their properties from them, and we now have beautiful parkland along the river in eastern Christchurch, where all these houses have now been demolished. So the total earthquake damage was about $40 billion, a third of which was related to liquefaction damage. So obviously significant hazard and something that it's important we understand. Now, what did this actually look like on the ground surface? So my PhD supervisor at the time was living in one of those worst affected areas. And after every event, he went out and took photos of his backyard. You can see September earthquake, about 0.2 G recorded in his backyard, liquefaction. The February earthquake, about 0.545 G. April earthquake, very minor liquefaction at about 0.15 G. Then we have the June 0.23 and 0.27 G, December 0.22 and 0.25 G. Putting a little surface trench through here after the June and December events, we can actually recognize distinct events preserved within these surface sand blows, comprising of an oxidized sand grading to a fine sand and capped by a silt drape. So it indicated that discrete events were recognizable, but it's debatable if these would actually be preserved in the geological record unless they were subject to rapid burial. Now, if you're slightly twisted or sort of involved in your backyard, such as my PhD supervisor was, you can even come up with a liquefaction triggering threshold for your backyard. So in this case, he's gone through all the earthquakes and the Canary earthquakes that caused liquefaction and didn't cause liquefaction in his backyard. When I'm talking about liquefaction, I'm talking about the surface manifestation of liquefaction rather than actually the triggering of liquefaction at depth. So he's now got a nice threshold for when he would expect to see liquefaction. So I talked a little bit about the distribution of liquefaction in Christchurch, but why did we actually see liquefaction where we did? Why was it consistently east of the central city? And what sediments do we have that make it conducive to such severe liquefaction? As I mentioned before, we've got the Braided River to the north of the city, which is the Waimakariri River. The city is built on the outwash plain of the river, so regularly it's avulsed across the surface of the plains, as you can see through the paleo channels marked in here. Within the city itself, we've got the CBD. To the east of the CBD, we've got a series of swamp deposits and coastal and nearshore marine deposits. So this reflects sea level transgression and regression following about the 6,500 before present high stand, which reached up to about here. We also have sands and silts deposited as the river regularly overtopped its channel during flood events. In the eastern suburbs, we also have low elevations and high groundwater tables, typically of about 1 to 2 meters depth. The loose sands to silts deposited as overbank flood deposits of the Waimakariri River, plus your nearshore marine and coastal sands to silts, combined with high water tables, make this area very susceptible to liquefaction. To the west of the city, we end up with a lot of gravels based on sort of the locations of the channels, and also higher elevations and deeper water tables. So obviously, as we're talking about at the start, sediments that are susceptible to liquefaction need to be saturated, and the closer they are to the surface, the easier it is for them to sort of exceed the overburden pressures and eject to the ground surface. So that's why we see to the east of the city more liquefaction. Now, taking a step back from Christchurch, hopefully all of you can start thinking about the cities that you may live in and settings that your sediments have been deposited under, and think, well, could I be sitting on liquefiable soil? How does this actually relate to where I live? It's not just a Christchurch specific problem. So when I think about the distribution of liquefaction in Christchurch, the fluvial geomorphologist in me sort of comes out, and I think back to my basic undergraduate training and all those hours spent looking at slides of depositional processes as meandering rivers migrate across their floodplain. And I can start to relate that to what we see in Christchurch. So you can see with the suburb of Avonside, we have a nice example of a meander bend. So if we think about the meandering rivers where we get erosion as the maximum flow direction reaches the outside bank, erosion of the bank, and subsequent transport and deposition on the inside bank. If over time, as this occurs, we end up with deposition of point bar deposits on the inside banks and outwards migration of the outside banks. So the outside banks typically comprise remnant, older, higher elevation ground, whereas the inside deposits are receiving your loosely consolidated, fine-grained deposits that are typically low elevation. In some cases, you can have your oxbow lakes, where your channel rapidly changes location following a flood event. So you can start to see the distribution of liquefaction here from the February earthquake. You start to pick up lateral spreading along the Avon River. Now, if we look at that in a bit more detail, we actually had a lot of post-event data sets following the Christchurch earthquakes. We've got, in the example here, we've got LiDAR-derived horizontal displacements, vertical displacements, both, and then we've got satellite-derived horizontal displacements as well, along with actual on the ground mapped liquefaction land damage and location of ground cracks. So this relates to properties as well. Combining these various different data sets, we can actually resolve the maximum inland extent of lateral spreading along with the occurrence of lateral spreading. Based on the various accuracies of the different data sets, we managed to come up with a line outlining the maximum inland extent of horizontal displacements greater than 0.5 meter. Overlaying the line from different data sets, we smoothed it and came up with a best fit line to show the occurrence of lateral spreading along the river. Now, we've ignored the sort of extent of the area as this starts to influence from estuarine deposits, and surface elevations aren't necessarily towards the river. We've got a series of paleo dunes and paleo estuary deposits that make it all a little bit more complicated. So this area enables just basic fluvial geomorphology to be examined in detail. The dotted lines that you can see represent areas of negligible to no lateral spreading adjacent to the riverbank. Hopefully you can start to see, if I go to the next slide, you can start to see this overlaid with geomorphology and also the location of the river. So areas where we get extensive spreading in from the river is generally on the inside of the riverbanks. If we think about as the flow comes around here, its maximum velocity is going to hit the bank here, erode deposits, and then we're going to get deposition on the inside, and same with these banks here. So really nice example of relating basic geomorphology to where liquefaction and lateral spreading occurs. And it sort of outlines how we can use geomorphology in assessing or first pass assessment of liquefaction and lateral spread assessments. But if we look at a little bit more detail in the suburb of Avonside, you have to start thinking about, well, as engineering geologists, unfortunately, that engineering part has to come in at some point, and we need to actually be able to quantify what we're talking about rather than just making big arm-waving statements about point bar and paleo channel deposits. Structural engineers and insurers like us to be able to put numbers to things, and we need to be able to design to something. So what I've got here is what I was showing before with the suburb of Avonside and that meander bend. So this is focusing on the inside of the meander bend. Each of these plots represent interpreted CPT traces. So the plots are assessed on the likelihood of liquefaction based on the Bollinger and Idris, I think it was 2014 method. Green means a less than 15% probability of liquefaction, whereas your red is getting up to 85% liquefaction probability. So what we can start to see for the September earthquake, we have the vectors showing the displacement magnitudes and directions. We can start to see, well, we get thick continuous liquefiable layers around the apex of the bend, and we get a lot of spreading towards these directions. We had very little spreading through here, as you can see from the vectors, and we've got very thin, discontinuous sort of liquefiable layers. Note this CPT here, where nothing is actually predicted to liquefy, but we do get lateral spreading in the area. I really like the CPT because it illustrates this area was governed by the overall liquefiable layer and the properties of the proximal sediments. And essentially this area was just, even if it had nothing liquefiable, it was just dragged along for the ride. So it's important to consider your overall system and what proximal CPTs are telling you, rather than just taking your one CPT and designing for that, because you're obviously not going to get the whole picture. If we then go to the February earthquake, so higher ground accelerations within the area resulted in much more widespread liquefaction triggering through the soil profile. And you can see, again, similar things where you've got thick continuous liquefiable layers, you get spreading, whereas again, the thinner layers resulted in less spreading. Note, spreading in this direction is not as severe as what we actually saw in the September event. Different reasons for this could be you've already fractured your crust, so you actually get more liquefaction ejecta, or you've already resulted in displacements that have affected that. But you do start to get more spreading in these areas here, where you've got thicker liquefiable layers coming through. You can also see sort of down in here where we've got a paleo channel that is sort of cut through along this cut bank here, and we get thick liquefiable deposits with extensive spreading towards the riverbank. So nice example of basic meandering river sort of geomorphology and how it relates to what we're actually seeing in the surface effects. If we look at this a little bit further, we can start to look at the thickness of liquefiable layers with distance from the river along transects. So here we have a transect of CPTs moving away from the river channel towards the maximum extent of lateral spreading. And we can see that the thickness of the liquefiable layer is sort of pinching and thinning along the profile, but is somewhat continuous, enabling this area to be rafted towards the river. Note that these profiles are for the February earthquake. And then what we see is areas where we've got no spreading, such as Transect 5, we have thinner and discontinuous layers. So we're not enabling rafting of the whole area towards the suburb. Some cases we do have liquefiable layers where we've got no spreading, but note that these are deeper and generally more discontinuous than what we see in other areas. Another interesting transect is Transect 3, where we've got no spreading adjacent to the river, but these vectors are actually showing we get spreading away from the river towards this topographic depression. And we can see as we move further away from the river, the thickness of liquefiable sediments is actually increasing. So this area here, you can see there's actually a channel based on the elevations that comes around the back here. So originally, the river flowed all the way around here, and it came up towards the north, but to enable improved rowing training on the river, they actually artificially cut this channel through here. So what we're seeing here is not the original riverbank. We're actually seeing a cut bank in the landform, and then there's some form of paleo swamp or deposition feature behind here where we're getting more liquefiable sediments. So really nicely illustrating how geomorphology is relating to what we're seeing on the ground surface. We can go through and quantify this further if we'd like, and we can look at the thickness of the liquefiable layers between areas that did and did not laterally spread or have displacements greater than 0.5 meter, and also between your recent fluvial deposits and your older terrace deposits. And we can see that if we look at the layer with a factor of safety less than 1, so in terms of this plot here, we'd be looking at the first layer we encounter that's potentially liquefiable. We see areas where we've got displacements greater than 0.5 meter have thicker liquefiable layers than areas that don't, which I guess makes sense. What the interesting point with this is we get large ranges in the values. What this is indicating is there's obviously spatial variability in the soils, and the soils aren't necessarily governed by single CPT properties like we get from a single cone, but are governed by the area-wide properties and how it sort of interacts with those liquefiable layers, and if we've got continuous fine sand layers throughout the region. Now, by this point in my research, we'd sort of wrapped up my PhD, was starting my postdoc, and it was like, I've got a nice story to tell, sort of a bit more time to wrap up all this research, some nice relationships coming out. Most of the work from Christchurch was sort of underway and repair was ongoing. And then 2016 hit and we had the 2016 magnitude 7.8 Kaikoura earthquake. This time during earthquake reconnaissance, we found there was a lot of liquefaction in the township of Blenheim, which is at the top of the South Island, so further north than Christchurch. And you can see here plotted on the map the distribution of liquefaction shown by the hatched symbol. So hopefully your eye is now getting a little bit trained in the morphology of meandering rivers, and you can start to see, well, actually there is some consistency in where we're starting to see these distributions. So generally on the inside of meander bends, we've got a nice little oxbow lake here, where it would have been adjacent to the point bar deposits. And then you've got some pictures here of what it actually looked like on the ground surface. Now, The fluvial geomorphologist in me, doing reconnaissance, very quickly sort of remembered this relationship and started picking out, well, based on reconnaissance, we want to target these areas here, document if there's something that happened, be interested to see if there's anything at these areas where we'd expect there to be no damage. At the time, I was doing reconnaissance work with geotechnical engineers, and for them, their world generally revolves around interpreting a single CPT, and they don't give much consideration to fluvial geomorphology. So they really hadn't started to think about this relationship with depositional settings, and they were just blindly driving around for days, seeing what would happen. So I think it's really important to note that we can learn a lot from each other, geotechnical engineers and engineering geologists, and actually understanding a landscape and applying geotechnical analyses to this can actually paint a bigger picture of what we're going to see following an earthquake, rather than sort of living in our own little separate bubbles. So by the time we got to the Kaikoura earthquake, we had some new data sets to play around with. Here we can see vertical displacements plotted up. You can see there's a meandering river sort of coming through here, the vectors showing directions of horizontal displacements. If we zoom into this area here, we can actually start to see we've got the white being the active channel of a meandering river, and we're getting distributions of lateral spreading and liquefaction adjacent to the river channel. So really nice example of basic fluvial geomorphology and observed surface damage. So if we start to look at this in a little bit more detail, we had a couple of sites that were sort of key investigation sites, one being the Marlborough Equestrian Centre, where there was linear arrays of sand boils and surface cracking. You can see that in the image here, they've been mapped out. None adjacent to the current river channels, but all adjacent to sort of this ditch running across the site. Looking through historical imagery, we can actually find out that this was part of a paleo channel associated with the former river, and it had actually been diverted during as part of the Wairau diversion construction to reduce flooding hazards in the area. So what we're starting to see here is that all on the inside of the paleo channel, so areas where we'd expect deposition of point bar deposits to be occurring. The next location I was talking about before was our Oxbow Lake. And you can start to see map distributions here where we've got liquefaction adjacent to the active river channel, but also concentrations where your paleo channel had been infilled with deposits and adjacent to your former river channel through here as well. So another nice example. The one that threw me though was this site here, which I showed in the initial image, where we had severe liquefaction and lateral spreading adjacent to the river. But this was adjacent to a relatively straight section of the river. In fact, it was a slightly outside meander bend of the river. You can see surface effects here were quite widespread. Then after we got back from reconnaissance, we'd sort of documented and spent too much time here. Someone actually pulled out historical imagery of the area, and we realized that actually from the image below, you can start to see, well, the position of the river channel in 1895 went exactly straight through the area where we were seeing liquefaction. So the distribution we were seeing at the site corresponded with the location of paleo channel deposits. So in terms of what we actually see at the surface, obviously really nice relationships between liquefiable or liquefaction and basic fluvial geomorphology. But what does this actually mean for interpretation of liquefaction hazards? So if we group our CBT traces, so what you're seeing here is the resistance of the soil with depth and the inferred soil type, is areas where we get liquefaction are generally characterized by relatively low density sands to silts close to the surface, whereas areas where we had no liquefaction observed generally exhibit more variability in the surface in the densities, as you can see by the variation in the wiggle traces from the CPTs, and also tend to be quite variable. So you can see there's a lot of sort of changes through here in the soil type. So they're not sort of those nice, clean, fine sand to silt deposits that we see as our fluvial deposits. We can actually overlay these traces. And so in here you can see red being CPT that did liquefy and blue being CPT that did from sites that didn't liquefy. And you can start to see what I was talking about before in terms of you can quite nicely fit almost a liquefiable trace to this, whereas the non-liquefiable trace tends to be a bit variable. So following on from the Christchurch earthquakes, there was a review into the Resource Management Act in New Zealand, which subsequently required all local councils to assess natural hazards that might affect their region. So naturally this incurred liquefaction. With this, the question came up of, well, what areas are susceptible to liquefaction? How are we going to assess this? And then the big question became, has this actually happened before? Digging through historical records, we found that there was upwards of 13 earthquakes prior to the 2010 earthquake that affected the Christchurch region that had caused liquefaction. We've since gone through and collated these into an online database. And what we found is the historical records generally indicated liquefaction was observed proximal to rivers. The records varied in terms of how we could spatially locate them. From the record you could see at the top there, where someone has sort of written a recollection of what they saw at someone's property or at a local feature within the neighbourhood, through to we get more recent events where we've got actual imagery of what was observed. So differences in the level of records, but consistent in sort of what they were recording. One example that came up with this is the 1987 Edgecombe earthquake. The distribution of liquefaction was nicely recorded following the event through reconnaissance mapping. And we can see the distribution in red here outlined with the distribution of previous river channels. So you can see in the background in blue the current location, and then we start to see the location of paleo channels through here. Again, you can hopefully start to see the distribution here is corresponding with the inside of meander bends across the area. Now, this was one of the areas where the liquefaction was assessed based on the conventional methods using CPTs with Idris and Boulanger 2014 and depth to groundwater models. These predicted widespread liquefaction across the city. We then went through and said, well, actually, we know there's been liquefaction before. If we assess these CPTs using back calculated PGAs and depth to groundwater models, do we actually predict what we observed from the event? And are our predictions consistent, or are we inadequately assessing the hazard for the area? What you can see here is the red dots representing CPTs where we've predicted moderate to severe liquefaction. And then the green is none to minor and orange is minor to moderate. So you can see that in some areas we're getting adequate predictions where we've observed liquefaction and are predicting liquefaction, but there's some areas specifically that within sort of near site 5 and 3 and 4 as well, where we're predicting severe manifestations of liquefaction, but we didn't actually observe anything. Now, being within the central township, we have photographs of these areas after the event and the minor damage that did occur in these areas. And there's definitely no images of surface flooding, and records indicate there was actually nothing observed. So it suggests these areas might be over predicting, but the question is why? So the first thing to do was, what can the subsurface tell us? So trenching through these areas, we found liquefaction features. So these were recognized as subvertical dikes. So you can see in the images here, these cross-cut the stratigraphy and aligned with surface features photographed on the site, maps on the site following the events. So we could say that these were features formed in the Edgecombe earthquake, and we knew that the sites that we were did liquefy during the Edgecombe earthquake. So these are sites 1 and 2 where liquefaction was observed. The key thing to note here is we didn't find anything predating the Edgecombe earthquake, but we think that this is actually a function of the young age of the soils rather than a lack of seismic events. Based on these being young fluvial sediments, there's quite a high seismic hazard for the region with a lot of proximal active faults. So trenching at sites 3, 4, and 5 revealed an absence of liquefaction features, indicating that surface manifestations at the area intersected within the trench didn't occur. So what else did we find with these sites? If we compare the stratigraphy that we found the sites 1 and 2 where liquefaction was observed generally had thick continuous deposits of sand and silt, whereas sites 3, 4, and 5 where liquefaction wasn't observed contained interlaid sands and silts. There was pumice granules in there and some fill as well. So that thin scale interlayering wasn't observed at sites 1 and 2, which was the main difference. If we think about where we are in terms of fluvial geomorphology, sites 1 and 2 being our point bar deposits, we would sort of expect continuous sands and silts being deposited. Sites 3 and 4 are sort of more in your distal floodplain, so you'd expect more of the interlayering soils deposited through thinner flood events. What can the CBT traces tell us? What we see at sites 1 and 2 is these thick layers of sort of low density soils. So these are shown in red with the layers that are predicted to liquefy based on the back calculated PG and depth to groundwater. We then have sort of interlayering of soils that are predicted to liquefy at sites 3 and 4. And at sites 5, we do have a thick layer that's potentially liquefiable, but that's at about 5 meters depth. And above that, we've got higher density sediments that appear interlayered. So if we look at the interlaying we're seeing in the trench, we're not really seeing exactly the same interlayering in the soils. So the question is sort of, is this relationship real? Is this something new, and has it happened before? If we go back to the Christchurch earthquakes, they did the same thing where they compared predicted land performance with that actually observed. And they found to the southwest of the city, there was areas of overprediction where severe liquefaction was predicted, but actually nothing occurred. Comparison with initial maps of the city, the black maps, indicated that these were mapped as swampland. And these are nicely corresponded with where we were seeing overprediction. Detailed boreholes done in the area, so Dames and Moore sampling, actually revealed what we can see here in the logs, and you can hopefully start to see in a bit of the images, was this very thin scale interlayering of silts, organics, and sands, which we spent days logging these very thin layers within the soils. Now, if we think about the CBT I showed you at the start, the diameter of that CBT, as it's being pushed into the ground and the force behind it, essentially it smears these layers together. So instead of recognizing the distinct soil properties, we just get a smeared sandy silt or a silty sand. So when I think about the process of liquefaction and liquefaction triggering, a sand is going to trigger at a different time to what we might have a silt trigger, or we might not trigger a silt to liquefy at all. So we start to get the systems responsive soils, which is missed in these interlayered deposits. So it is quite understandable that we can have overprediction within these interlayered deposits. But if we start to think about where it's occurring, well, where do we get interlayered deposits? Typically swamps make sense, distal floodplains, areas receiving small amounts of sediments repeatedly over time compared to sort of thick blanketing layers of fine sand. So the question is, how can we actually recognize this and how can we actually use this? A side note to this is, well, yes, it's all well and good to have all these liquefaction features and catalog all these features, but how often does this actually occur, and do we actually need to be thinking about this? So trenching in the worst affected areas in Christchurch, we actually found that Canterbury earthquake features aligned and cross-cut features that predated the Canterbury earthquake sequence. So you can see here these dikes that I was talking about before from Whakatane that come up and cut through this subsurface deposits and align with surface features observed at the surface. A really nice example here where you've got that grey sand you see at the surface being one event, it actually cross-cut another grey sand indicating a second Canterbury earthquake sequence event. And then on the outside, we had this oxidized fine sand layer with the same morphology as the Canterbury earthquake sequence features, but also had a mottling and biodistribution of the boundaries. So indicating it'd been in place within the soil for a longer time. Now, dating of these features is difficult because the sediment within the feature represents the liquefied source at depth. So you can't date the features themselves. You have to date the boundary stratigraphy based on where they reach in the soil profile. But doing this for areas within Eastern Christchurch revealed that sort of within the last 200 years or so, we think there was a liquefaction triggering event. And therefore, the main thing it indicates is that development within these areas actually took place on soils containing evidence for previous events of liquefaction. So it could be recognized that these soils were prone to liquefaction based both on geomorphic setting and also paleoliquefaction trenching. We can then go a little bit further with this paleoliquefaction work, and we can say, well, we know that these soils have liquefied. If we can find out which layer has liquefied, and we can use our CPT, we can go back and say, well, assuming that this had a factor of safety less than 1, meaning it triggered liquefaction, what combination of PGA do we need to actually trigger liquefaction? From there, we can say, well, what is the return times of PGA exceeding a given threshold for triggering liquefaction at a site? And that can help to inform our seismic assessment and our hazard assessment for the area. So a few different things you can do based on how much you want to get involved down that route, but still interesting and important for hazard assessments. So how can we actually apply this? Obviously, it's all well and good me waving about depositional settings and CPT results, but obviously at the end of the day, we need to sort of quantify something and put something on paper. In New Zealand, we've come up with a series of liquefaction guidelines for liquefaction hazard assessments, and these are based on the number of in situ testing we have for the area, based on a very basic desktop assessment. We're using geomorphology and sort of depth to groundwater data, and maybe a few in situ tests, all the way up to where you have sort of scattered CPTs every few properties within the area, and you'd often do that for sort of a site to small area wide investigation. We can also think about landforms that we'd think would be susceptible to liquefaction, obviously based on depositional characteristics. We've got rivers and streams and lakes. We've got coastal margins, estuaries and swamps, reclamation fields and tailings dams. So it's important at this step that the geologist can sort of take a step back and think, well, instead of getting lost in the detail of my CPT, what can the landscape actually tell me about what I might be looking at? So hopefully after this talk today, you might view this image in a different way. You've obviously got a series of CPTs scattered across the site. You've got a stream channel, as you can recognize as a deposition running through here. Would you take one CPT, for example, here, and design your properties for it? Would you request more testing to be done near your paleo channel? Or to the trained eye, you might start to see all these little splays coming off here as well. Do you think they're paleo channel deposits? Or how is the area going to perform in an earthquake? So it's important, I always sort of stress the importance that never take a CPT in isolation or never take an assessment in isolation. Always think about what can the surrounding soils tell you about the overall properties of the area. We can then group the CPTs together and start to think, well, how does it fit based on what we're looking at before? Do I have a clean profile of low density fine sands to silts close to the surface with a shallow groundwater table where I might think liquefaction would occur? Or I might be seeing lots of variability when I lump all my CPTs together, indicating interlayer deposits, and maybe I'm over predicting or don't have consistency in my liquefiable layers. So conclusions from this, obviously we've seen that events within New Zealand have really clearly outlined that liquefaction and lateral spreading is predominantly reported proximal to rivers and streams. And this typically corresponds with point bar and paleochannel deposits. Note that this relationship is really observed clearly at low PGA, so about 0.1 to 0.2 G. As the shaking intensities increase, we start to liquefy more of the soil profile. And as we saw from Christchurch, liquefaction becomes a bit more widespread. Obviously, as a first pass tool, geomorphic mapping is really important to identify susceptible deposits. And it's important to understand the geomorphic setting when interpreting your CBT. We also saw that inconsistent predictions can be highlighted from comparison of post-event observations with that predicted from the simplified liquefaction triggering methodologies. You can verify your liquefaction hazard through trenching, which is a very low-cost methodology. It's just digging a hole, but having a trained eye look at it. And then inconsistent predictions are closely corresponding with the depositional settings of the subsurface deposits. And I'll leave you the image on the side, which is the realities of trenching in red zone deposits with potential asbestos contamination. So it's not all fun and games. And finally, got a few people to thank for their help with this work. So thank you, and thank you again, Stratus and YEG and IAG for the opportunity. And I think if there's any questions, I've seen these chats that have been popping up, so haven't seen what they are yet.
So thank you very much, Sarah, for this informative presentation. I think most of the people, they got really fascinated with that. There's one question from Tumaika Kocha. Is there a threshold soil depth for liquefaction investigation which would not cause surface damage? In your study, 10 meters?
So that's an interesting question, and it's very much open to debate. There's some people that are of the belief that you should continue a CBT until refusal. There's definitely been cases of liquefaction up to sort of 20 meters depth. There is a nice relationship by Ishihara, who is sort of the first person to talk about liquefaction, a Japanese researcher, that compares the thickness of the liquefiable layer to the thickness of the overlying non-liquefiable layer. And the general ratio for getting surface effects of liquefaction is 1-to-1. So where the thickness of your liquefiable layers exceeds the overlaying non-liquefiable layer, you generally get liquefaction at the surface. But definitely when we're assessing liquefaction, we just go 20 plus meters, as deep as our CBT will take us, and assess the whole soil profile. So no, there's not a cutoff depth that I would say. It's more recognizing your soil properties.
Yeah, exactly. Yeah, that was really fascinating. So, is there any other question that you would like to pose, probably to Sarah Bennett or Bastin or to Tim Nash? I will give like a couple of seconds. Sarah, I have a question about what do you think about the validity of the ISN model that you used in your study?
Which model was that, sorry?
The model. Is it something like called ISN?
The triggering threshold,
Yeah.
The Bollinger Idris.
Yeah.
So I mean, it's widely used, and every method has its limitations, but it's, in terms of industry recognized methods, it's most widely accepted, and it's easy and quick to do. We could go on for days debating the finer points of the accuracies and limitations, but I think it's the best tool that we currently have for this, unless we want to sort of go into effective stress analysis and all those other detailed engineering assessment methods. So that's sort of, my view on it is it's the best we have, but also don't necessarily believe what your model spits out. Think about if it makes sense and what you're actually looking at.
Yeah, exactly. Yeah. So I don't know if there are any other questions, either for Dr. Sarah or for Tim. One moment to check also. No, so I would like to thank both presenters for their presence in today's e-YEG webinar. It was our pleasure to have both of you, and especially have the industrial part, because last time we had the academic part and now we have the industrial part. It was really informative, especially both of you with your cases. I would like to thank all the attendees for today's presence. And just to point it out that e-YEG webinars will continue in a monthly. So please feel free to follow us on our social media and on our YouTube account in order to follow up our webinars. Once again, thank you very much, Tim. Thank you very much, Sarah. Good luck and hope everything goes smoothly with the whole situation of coronavirus and stuff.
Thank you, Stratus. Thank you, Sarah. Thank you, IAG.
Thank you, everyone. Thank you, everyone, for being here. Thank you.